Imaginary numbers. The idea that revolutionized math and physics, opening doors to calculations and discoveries that once seemed impossible. For centuries, mathematicians believed that if an equation required the square root of a negative number, then the solution simply does not exist. Back then, math was represented with words, algebra, and even drawings. Imagine writing the expression x squared as the area of a square with sides of length x. It wasn't until the 1600s that modern mathematical notation began to take shape, paving the way for more abstract concepts. So today, we're going to explore the concept of imaginary numbers in detail. In my opinion, to better understand imaginary numbers, you have to take a step back and take a look at negative numbers. Negative numbers were once as puzzling as imaginary numbers are to us today. Picture yourself as a mathematician in the 1700s. You easily accept that 2 minus 1 equals 1. But then, if someone asks, what about 1 minus 2? To solve this, mathematicians invented negative numbers, a useful fiction that, although intangible, helped describe relationships like depth, indicate elevations beneath sea level, record financial losses, and even show movement in the opposite direction along a coordinate axis. Clearly, as science and technology advanced, we found more practical applications for negative numbers, which made understanding them much easier. Similarly, the concept of imaginary numbers was born out of necessity. Just as negative numbers weren't initially easy to intuition, many mathematicians were skeptical about the existence of imaginary numbers. Fast forward to today, imaginary numbers are a cornerstone of advanced physics and engineering. You might wonder, why don't we introduce them in early math classes? The reason is simple. Its true power reveals itself mostly when we face complex mathematical challenges. As math and physics evolve, we discover countless beneficial uses of imaginary numbers. Their applications, from solving quadratic equations to describing wave and quantum mechanics, make them indispensable in modern science. You might not believe in imaginary numbers at first, but remember, if negative numbers can go from being confusing to crucial, imaginary numbers will eventually feel just as natural. Now that we explored the evolution of mathematical ideas, let's dive into why imaginary numbers are not just mathematical curiosity, but a powerful tool with many applications. Imaginary numbers were originally created to fill a gap in our number system. When mathematicians encounter equations that involve taking the square root of negative numbers, like the quadratic equation x squared plus 1 equals 0, they found that real numbers alone wouldn't do. By introducing imaginary numbers, or usually referred to by using I, they could express the solutions of these otherwise unsolvable equations. But that's just the beginning. Imaginary numbers extend our mathematical toolkit in several key ways. When you solve a quadratic equation, you sometimes end up with a negative value under the square root. The introduction of I allows us to express these solutions neatly. The idea even scales up to cubic and higher order equations, giving us a complete set of solutions that would be impossible to describe using just real numbers. Imagine you are asked to find the solution for x squared equals 4. In a real number system, the solutions are either x equals 2 or x equals negative 2, because both 2 to the power of 2 and negative 2 to the power of 2 equal 4. Now, consider the equation x squared equals negative 4. If we only use real numbers, there is no solution because the square root of any real number is always non-negative. However, by defining I such that I squared equals negative 1, we can rewrite the equation as x squared equals 4 times negative 1. Then, as we take the square root of both sides, we find that x equals plus or minus 2 times I. This simple example shows how the introduction of imaginary numbers provides solutions that wouldn't exist before. While it might seem like a small technicality, These solutions are extremely useful in fields like electrical engineering and quantum physics. Before we explore these applications, let's first understand another remarkable property of imaginary numbers. One of the most critical benefits of imaginary numbers is how they allow us to represent rotations. To see this in action, consider the cyclic nature of I, where I to the power of 1 is just I to the power of 2 is negative 1, I to the power of 3 is negative I to the power of 4 is 1, and then the cycle repeats every 4 powers. This cycle isn't just a numerical curiosity, it has a deep geometric meaning. When you plot numbers on the complex plane, with the horizontal axis representing the real numbers and the vertical axis representing the imaginary numbers, multiplying by I corresponds to a rotation of 90 degrees counterclockwise. The rotational property is crucial in several advanced fields. For example, in physics, the ability to rotate a vector by a fixed angle is invaluable. It helps us understand phenomena like interference and resonance. By extending our number system to include I and its properties, we not only solve more equations, but also gain a powerful tool for visualizing and understanding dynamic systems. I hope that this video helps you better understand the concept of imaginary numbers. If you have questions, please leave them in the comments. Don't forget to like and subscribe to our channel. Thanks for watching.